Hello, everyone. Thank you so much for joining me again. Today, we're going to talk about Newton's second law, building on our unit about forces in general and about Newton's laws more specifically. We're building today from what we talked about last time of Newton's first law, which remember we talked about as inertia. So, reminder, the readings you should do for this section come from two of our textbooks, Understanding Physics Chapter 3, Sections 4 through 6, and then Conceptual Physics Fundamentals, Chapter 4, Section 2. Newton's first law explains what happens to an object that has no net force acting on it. The object either remains at rest or continues moving in a straight line with constant speed. Remember, inertia. Newton's second law answers the question of what happens to an object that does have a net force acting on it. So imagine pushing a block of ice across a frictionless horizontal surface. So here's our block of ice. When you exert some horizontal force on the block, it moves with an acceleration of, say, 2 meters per second squared. If you apply a force that's twice as large as our initial force, the acceleration then doubles to 4 meters per second. If we push 3 times as hard, that triples our acceleration, 4 times as hard, 4 times the acceleration, and so on. From this observation, we can conclude that the acceleration of an object is directly proportional to the net force acting on it. It's important to note that the mass of an object also affects acceleration. So suppose you take our 2 ice blocks and you stack them directly on top of each other, and then we push them with a constant force. If the force applied to that one block has an acceleration of 2 meters per second squared, then the acceleration when we have 2 blocks on top of each other drops to half that value, or only 1 meter per second squared. You can see down in this corner. So when the 2 blocks are pushed, we have 1/3 the initial value when 3 blocks are then pushed. So you can see that the acceleration of an object is inversely proportional to its mass. So let's put this in mathematical terms. We have our 2 relationships we just discovered, that the force is directly proportional to the acceleration and that the mass is inversely proportional to the acceleration. So then mathematically we can conclude that if the acceleration is proportional to force and inversely proportional to mass, that the acceleration is equal to the force divided by the mass. So then if we're going to rewrite it into a different form, we can get Newton's second law, which is the net force acting on an object is equal to its mass times its acceleration. So F equals ma. It's important to know that force and mass also have an interaction going on. It's not just force and acceleration or mass and acceleration. We know that the mass of an object is not about how heavy it is. Remember when we talked about that during kinematics? The mass of an object is its resistance to change. So weight describes how heavy an object is, but weight is a force, not a mass. And we think of it as the force of gravity acting on an object. So your weight is actually how much the earth is pulling down on your mass. In this case, the force due to gravity, or your weight, is equal to your mass times the acceleration due to gravity. And remember, the acceleration due to gravity is 9.8 meters per second squared. We talked about that back when we were doing kinematics as well. So if an object has a mass of 90 kilograms, or it has 90 kilograms of resistance to being changed, because from Newton's first law, an object at rest wants to stay at rest, then we have its force due to gravity, or its weight, of 90 kilograms times 9.8 meters per second, which gives us a weight of 882 kilograms times meter per second squared. Kilogram meters per second squared is our unit of force, and we rewrite it as a Newton, a capital N. So 1 Newton is equal to 1 kilogram meter per second squared. Now that we've talked about what Newton's second law is and done a quick example, before we do some more examples, we're going to think about this theoretically. Remember to pause the video after each question to reflect on it and come up with an answer for yourself before hearing what the answer is. So we have 5 true-false questions in our first one. If an object isn't accelerating, no external force is acting on it. This is true if the resultant force on an object is 0, either because there's no forces present or the sum of the forces is 0. The object can still move with a constant velocity. F equals ma tells us nothing for certain about what is happening with velocity. Our second one, if an object isn't moving, no external force acts on it. This one's false. An object that remains at rest has 0 acceleration. However, any number of external forces could be acting on it, provided that the sum of these forces is 0. Our third one, if a single force acts on an object, the object accelerates. This is true. When a single force acts, the resultant force can't be 0 and the object must accelerate. For number 4, if an object accelerates, at least one force is acting on it. This one is directly related to number 3, and it's true. When an object is accelerating, at least one force must be acting on it. And we have to have a non-zero sum of forces, so there could be more. And finally, if the net force acting on an object is in the positive x direction, the object moves only in the positive x direction. This one is false. If the net force is in the positive x direction, the acceleration will be in the positive x direction. However, the velocity of an object does not have to be in the same direction as its acceleration. Consider the motion of a projectile. Remember what was happening when we had projectile motion. Let's do some quick examples. First, we have a 900 kilogram car accelerating from rest to 50 kilometers per hour in 10 seconds. I've already done the conversion for you. 50 kilometers per hour is equal to 13.9 meters per second. What is the net force on the car? So in this problem, we have our mass, we have our change in velocity, and we have our change in time. What we don't have is the acceleration to find our force. So first we need to find the acceleration. And to do that, remember, it's the change in velocity over the change in time. So we're going from 0 to 13.9 meters per second in 10 seconds. So we divide 13.9 divided by 10, and we have 1.39 meters per second squared. Now we have an acceleration, and we have the mass of our car, so we can find the net force, which is F equals ma. So 900 kilograms times 1.39 meters per second squared gives us 1,251 newtons acting on the car. All right, so for this example, we have a force acting on 2 kilograms, and it gives an acceleration of 3 meters per second squared. What acceleration is produced by the same force when acting on a mass of 1 kilogram? And then what if we have a 4 kilogram mass instead of our 1 kilogram mass? So first we need to find the force acting on this 2 kilogram mass. And we have F equals ma is equal to 2 kilograms times 3 meters per second squared for a force of 6 newtons. Now we want to take that same 6 newtons and apply it to this mass of 1 kilogram. It's going to have a different acceleration, and we're going to find that by rearranging F equals ma. So we have a is equal to F over m, or 6 newtons divided by 1 kilogram. So we get an acceleration of 6 meters per second squared. Now for our 4 kilograms, we're using that same rearranged equation, where now we have 6 newtons over 4 kilograms, and we have 1.5 meters per second squared for this acceleration, which makes sense because when we have a larger mass, we will have a smaller acceleration if we have the same force. And now that we've talked through what Newton's first law is, we've thought theoretically about it, and we've done some examples, I want you to take a step to get ready for class. And remember, when we started our unit on forces, we had this diagram where we have the Hulk pulling on 2 different carts, and we're going to break it down piece by piece. And now we're going to start thinking about how it works mathematically after we've done our force diagrams. So, in preparation for class, what I want you to think about is what is the weight of the red cart in newtons? And we're going to start class with this problem. So if you have questions, come prepared for those. Thank you very much, and I look forward to seeing you all in class.